Yeah, very good morning. Am I audible?
Yes, sir.
Okay. Let me start. Are you able to see the screen?
Yes, sir.
Okay, that's great. Fine. Okay. So, any question so far? We have no don't have any class in the last week, right? We didn't have, right? So, how was the tutorial? Hello, am I audible?
Yes, sir, you are audible. Yeah, the tutorial was solved 4 questions.
Okay, fine. And are you able to get the concepts? Means like how you will approach the problem if its problem is given to you, and suppose you are want to discuss the continuity and the existence of limit in two variables or three variables. Now, are you able to do it now? Yeah. Please give quick answers. It's very tough to manage on in life. I can't see your faces. Yeah. Yes, all of you can speak, right? Or my voice is not coming. Yeah. Am I audible?
Sir,
Yes. Am I audible to all?
yes, sir. Sir, tutor taught us about the two variables and the sum of the three variables. There is a little bit confusion, so we
Okay.
cannot get it with three variables. And
Okay.
there is a new formula as well.
New
For
formula.
yeah,
Yes.
for differentiability. Like in
Oh,
the last problem,
differentiability.
yeah, sorry,
Okay. Okay.
differentiate.
Okay.
We
Okay. Okay.
stuck in
Okay.
the last
Yeah.
problem. Uh,
Yes, yes, fine, 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 fine. I think we have only completed and partial derivative till now. Okay, and we have not completed the differentiability, but I was in the impression that differentiability also has completed. Okay, so today we completed differentiability and we'll see. Okay, or she also talked with me and she said that she will post the detailed solution about it, and or maybe in the next tutorial she will do explain that. Okay, and accept the differentiability concept means I think this finding partial derivatives with respect to x, let's say this first problem and this second problem. Any student is having any confusion regarding these any of these four problems? Let me ask this first. Means, are you able to comfortably do partial derivatives with respect to x, with respect to y? So if you do differentiate with respect to x, treat y as a constant. Differentiation with respect to y, treat x as a constant. Yeah, so anyone has any kind of doubt, okay, regarding how to find the partial derivative? Are you able to differentiate? Means the partial derivative already explained, you are differentiating in one dimension. Okay, keeping other dimension is constant. Yeah, fine. So okay, now okay, let's start the lecture and let's see. Uh, okay, which question number 4? Question number 4 is in this example or question number 4 in the tutorial sheet?
In tutorial sheet, it was like including
That is a differentiability.
yeah, that was differentiability, and there was f of x, y, z, and
Yeah. Hmm.
thing was only written in x and y.
Okay. So I
Previous.
have been, let's see, this question number 4. If I just quickly try to give you the overview about it, how to solve this. So we are supposed to find this zx means dou z by dou x means z is differentiated partially with respect to x. And you have been given with this equation how this z and x and y are related. So this is given to you that yz minus ln z is equals to x plus y. This is given to you. And what is given other is defines z as a function of the two independent variables x and y and the partial derivative exists. So see, whenever it is given that find zx, if the equation this defines z as a function of the two independent variables x and y and the partial derivative exists, means is pre-assumed that if you're going to differentiate partially with respect to x or with respect to y, okay, then this you are assuming first is the partial derivative exists and you are start doing it. Okay, another thing is here, like in the previous questions, first, second, and third, you have clearly told what is f. What is f? Is f is a function of two variable x and y. Now here z will play the role of f. Okay, here is the clear expression f of xy equals to so and so. But here it is not, like z of x comma y is equals to so and so as a function of x and y only. It is a kind of implicit. Okay, right. So it's not a explicit one. Okay, so here is a implicit. So now, so here you have to be careful when you are going to differentiating partially with respect to x. Okay, I will do that. You can do similar fashion partial derivative with respect to y. So keep in mind that z is a function of x comma y. Okay, so zx will means you have to find zx. Okay, so I wish to do this. So these are given things. Okay, so I'm going to differentiate one. Okay, I'm differentiating one partially with respect to x. So other variable, independent variable, I'm telling you, you have to treat as a constant, not dependent. Okay, that must be clear to you. Okay, so here y should be treated as a constant, not z, when you're differentiating partially with respect to x. Okay, so when you're differentiating, so let's take first term. Okay, so if you differentiate partially with respect to x, y into the derivative of z with respect to x, that is zx, plus z time partial derivative of y with respect to x, that is 0. Y is a yet right, y is a constant whenever you're differentiating partially with respect to x. Now this is about the first term. Now about the second term, you have ln of z. How will you differentiate? It's going to be kind of composition. Okay, so first you have to differentiate ln, that is 1 by z. Now then you have to differentiate argument, that is into zx, is equals to the right hand side. Now differentiating partially with respect to x, the first term is 1, and differentiating partially with respect to x, the second term is 0. Okay, so what you observe is now y into zx minus 1 by z into zx. So I may write minus 1 by z times zx is equals to 1. So now you can means you can write it down like zx equals to. Now if you solve it out, it is going to be z divided by y times z minus 1. So this is what the expression for zx. Similarly, you can differentiate partially with respect to y. Okay, right. Now, once now let's go ahead now. Okay, suppose you have been given that the partial derivative exists. Okay, in both the variable, you take a function f of x comma y. Okay, and you are talking when you are talking about the derivative, you are talking about at a point x naught y naught. Okay, suppose the partial derivative exists at x naught comma y naught in the both direction, x direction as well as y direction. Can I guarantee that function is continuous at least? Okay, we will talk about the differentiability later. Okay, so my question is now, if let fx and fy exist at x naught y naught for f of xy. So whether in this case f is continuous at x naught y naught. Okay, that we can expect, but the answer is not true in general. Okay, so I have an example here. Okay, so this is not true in general. So with this example, we can show that clearly function is not continuous at 0. Can I say that? This given f is not continuous at 0. Right? Can I say that? Because f at 0, 0 is 1. Okay, so you can see f at 0, 0 from this definition, this value of f is 1. But if you look at the limit, okay, limit of x comma y as tends to 0, 0, okay, f of and also you can show, okay, you can also show that I have been given with the f is equals to 0 if x into y is non-zero, and 1 if x into y equals to 0. So from here, the definition, it is very clear that f at 0, 0 is 1. Okay, either x is 0 or y is 0 or both together 0. The value of f is 1. Another case is limit. Limit of x, y tends to 0, 0, f of x comma y. That is going to be the limit. Okay, that's going to be limit is 0. Can I say this? You have done many examples now, right? You can reach along any path. Okay, you can reach along any path. See, y equals to, let's say, mx. Okay, so you can decide the limit, right? So you have, you can take, let's say, y equals to mx. So, okay, now what it will be, mx is means like if y is non-zero, x is also non-zero, right? If y is not 0, x is also not 0. I'm taking m is non-zero. At 0, 0 point, you know, right? What is the value is 1. Okay, either x is 0 or y is 0, f is 1. Or both are 0, then f is value is 1. So along this path, okay, what is limit of x comma mx tending to 0, 0, f of x comma mx. So, you know, right, what is that? What is the definition of this now? M into, so if you look at what is the value of this function for any x non-zero is x into, you can see it is going to be satisfying this condition. At any point, this is going to be 0. Similarly, you can look at along any parabolic path. y equals to mx square. Okay, you can look at any cubic path. Okay, and so on. Now, what finally you can show also that you can take this with L is 0. F value is also 0, and you can take any delta. Okay, so if you want to go with the epsilon delta definition, you can choose L equals to 0. Now, mod of f of x comma y minus L. Okay, mod of f of x comma y minus L. I want less than epsilon whenever 0 less than square root of x square plus y square is less than delta. Now L equals to 0 and let's say epsilon bigger than 0 be given. Okay, so L is 0, epsilon greater than 0 be given. For any point, so you can choose delta equals to epsilon here. Okay, that artificial delta or artificial epsilon, both are the same thing. For given epsilon, you can choose this that same as delta, for which this condition is true, because this left hand side is always 0 because f of x comma y is 0. Right? On now along x-axis and along y-axis, right? So along x-axis and along y-axis, what it will be? Okay, so this is what these are the straight line passing through the origin. Okay, this is along the x-axis and along y-axis. What we can say? This will satisfy this, right? Equals to 1. Yes. Okay. Yes. I think limit is here. What we have observed now. Okay, I've got this. Whenever you have this is going to be x comma y is whenever you have x into y is non-zero. Okay, I have discussed this case. Now, what I observe now from the example is when you have along x-axis. Oh, I found that this limit does not exist even, right? So along x-axis, what is the value of f? F of x comma y is 1. Right? Along x-axis, the value of f of xy is 1. Why? Because y is 0 and it will satisfy the condition x into y is 0. Right? So our assumption that L is going to be 0, that epsilon greater than 0 be given, this is wrong. Okay, so that is not going to be true. So this is how you have to look at other problem. Okay, you have to look at carefully that what are the paths. So it's not only the point 0 0. If it is given that x on if I redefine this function, okay, if I redefine this function like suppose this definition, instead of this, if I give you that x into y is or x comma y is a 0 0 point, then the situation will be different. Now, but this is not the case here. Okay, so this here what it also carry forward is along x-axis, along y-axis, the value of f is 1. Okay, so limit of constant is the constant itself. So what it gives me that along x-axis f of xy is 1. So this will give you, this implies limit x tends to 0 f of x comma y equals to 0. Okay, x comma 0, right? Along x-axis y is 0, that is value is 1. Similarly, you can also show that limit y tends to 0 f of 0 comma y is 1, right? Now, and along the line y equals to x, you have along the line y equals to x. What is that? Limit x tends to 0 or y tends to 0, whatever. Okay. F of x comma x. The value of this is x square, right? Y equals to x square, where we are talking about the non-zero values on the line. So this value is all are 0 only. So limiting value is 0. So 1 is different from 0. So the limit does not exist even at 0, 0. So we can't say the continuity. Okay. Now the question is whether partial derivative, because this is what we want to show. Okay, then if partial derivative exists, we can't guarantee that f is continuous at that point. Now you have to see what is the partial derivative at 0, 0, both fx, f and fy. Okay, so let me give you that now. So you have f is, I'm rewriting the function here, and I want to find what is the partial derivative 0 if x into y is non-zero, 1 if x into y is 0. Now I'm interested in finding the fx at 0, 0. What is the definition? Limit h tends to 0, f of, so if I recall, let me write down first time here. Okay, I go that x naught comma y naught. What is that? X naught plus h comma y naught minus f of x naught comma y naught divided by h. Now what we are interested in, fx at 0, 0, that is going to be a limit h tends to 0, f at x naught y naught is 0, so h comma 0 minus f at 0 comma 0 divided by h. Now if you look at the numerator carefully, f at 0, 0 value is 1. Just now we have seen. Okay, f at h comma 0, it satisfies this condition. Still it is going to be 1. Okay, for any h greater than 0. So it is a 1 minus 1, that is 0 by h. So 0 by h is 0. Okay, so this complete term is going to be vanished. Okay, and limiting value is also 0. So partial derivative of f with respect to x at 0, 0 exists and equals to value is 0. Similarly, you can show now similarly, I can say fy at 0 comma 0 is going to be limit k tends to 0 f of 0 comma in the y direction 0 plus k minus f at 0 comma 0 divided by k. And now again by the similar concept, f at 0, 0 is 1, f at 0 comma k is also 1. So it is a, I just write this step here, which we have not written, that's 1 minus 1 by k. So that is going to be 0. So partial derivative both exist at 0, 0, and but the limit of f at 0, 0 does not exist at all. Okay, so limit does not exist means the function is not continuous at 0, 0. So the existence of the partial derivative does not guarantee the continuity of the function. Okay, right. Now, so what will be the means like then how we will compensate it? Okay, means what is the additional condition required? Okay, or is or are. Okay, maybe there may be more than 1 or 2 conditions required on partial derivative or function f, so that you can guarantee that the function is continuous at that point. Because in the single variable case, we have already seen that differentiability implies continuity. So it also shows some necessity of defining the differentiability in the 2 variable cases. Okay, and which will give you the you can say the generalization of derivative in single variable to more than 1 variables. Okay, right. So okay, fine. Okay, so what is another thing is I want to show you is sometime it may also possible, okay, sometime it may also possible for you that suppose everything is fine, partial derivative exists, and suppose you addition in some other condition, okay, you may also expect that if you go with the higher order derivative, let's say f of xy is given to you, okay, some function, okay, you may also expect it that f x y, you do it, order doesn't matter, okay, you may expect that at a comma b, okay, some point a comma b, both are the same thing, means first you differentiate partially with respect to x and then with respect to y, or first with respect to y with then with respect to x, both will come, but this is not true in general, means again it again requires some additional condition on f, mean, right? So you differentiate partially in any order doesn't mean that they are going to be the same, converge to the same value, okay. So here I have one example for you that which shows that f at you first differentiate partially with respect to x, then with respect to y, and evaluate the derivative at the partial derivative at this point 0 0, or in the reverse order at 0 0, both are not going to be coming to the same, okay, right? So let me explain this example, it's very simple here now, okay, because you are going to identify the second order now partial derivative. So this can be seen that if you go with the more higher order derivative, the situation will also more critical, okay. That means means you differentiate 2 times with respect to x and 1 time with respect to y, okay, and then you have 2 time or we can talk about like 2 time differentiation with respect to x and 2 time differentiation with respect to y in one order, in one side. Another side is, let's say, first 2 time differentiation with respect to y and then 2 time differentiation with respect to x. So you can see that that may also not be the same, okay. So that is also going to be follow up in the same fashion, okay, that in general, okay, you can't expect the nice things to happen, okay. So you need to have some additional condition on the function, okay, and sometime it is very much required, okay, when you look at some applications, okay. So now you are given with the function definition is f of x comma y is equals to x into y times x square minus y square divided by x square plus y square. So whenever x into y is non-zero, or not means xy is a not origin, okay, and it is 0 whenever x comma y is at 0 0. Now I'm leaving to you to verify that this function is continuous, okay, this function is continuous at 0 0 point, okay. I'm leaving that case to you, okay, that, okay, verify that f is continuous, okay, at 0 0. Okay, it will be very simple. You can look at along the path y equals to mx, y equals to mx square, and so on, okay, and then try to identify the epsilon and delta, okay. So first you have to verify that f is continuous at 0 0. Secondly, you can also verify that first order fx, second order first order fy, okay, they are also exist at 0 0, exist at 0 0, means all a higher order derivative also you can fx fy yx, at least fxy exists at 0 0, that also can be verified. Now what I'm going to do is, now once f is continuous, I'm going to differentiate partially with respect to x and partially with respect to y, okay, and then we'll see what is going to happen. So your means for x comma y is non-zero. I have the definition is f is going to be f of x comma y is equals to x into y time x square minus y square divided by x square plus y square. Now differentiate partially with respect to x. Okay, so what is fx is going to be? Now you have to take product rule, right? X into y and so on. Okay, so first is y into x square minus y square divided by x square plus y square into the derivative of x with respect to x, that is 1, plus now x into the derivative of this. Okay, y is a constant when you differentiate partially with respect to x. Now you have to differentiate this rational term. Okay, so you have to use the quotient rule here. Okay, so that is going to be x square plus y square whole square to have, right, x square plus y square time 2x plus x square, not plus here, minus x square minus y square time 2x, right? So this is going to be simple is fx equals to y time, the first term is x square minus y square divided by x square plus y square, and second term is now 2x is common. Okay, 2x is common. Now x square plus y square minus x square minus y square, so x square will get cancelled, so y square plus y square, that is 2y square, so 4 times x y square, right? So plus x into y is also there, so 4x times y square times x into y. Okay, 4 times x y square into x into y divide by x square plus y square whole square. Okay, now you can take further LCM, that x square plus y square whole square as an LCM here. Okay, and what you will observe is here is y time x square minus y square into x square plus y square, that is x to the power 4 minus y to the power 4 plus 4x square y cube, right? But whether this will help you to simplify? No. Okay, let it be. Okay, so this is going to be, so I'm going to write down this in a simple form now. So this is here, I can actually replace it now with 4 times x square y cube. Okay, right. Now, what is fy? Fy, you have to differentiate partially with respect to y. Okay, so you are having this one now. Again, you have to follow the similar manner. Okay, but since some things will change here in the second term. Okay, so the first term will be x into x square minus y square divided by x square plus y square, and second term is you have xy time, you have x square plus y square whole square time, here is x square plus y square time minus 2y, right? Okay, and minus x square minus y square time 2y. Okay, now this is going to be x, I'm writing the simplified form, x square minus y square divided by x square plus y square plus, now again 2y will be come out. Now here is minus x square minus y square minus x square plus y square, so y square will get cancelled here. Okay, and 4 times, so write 2y square here and 2 here is 2y, right? So 2y is out. So this is going to be 2x y square time. Here is going to be with minus sign, minus 2y square, right? So that is divided by x square plus y square whole square. So here it is going to be, yes, right. This is x, 2y is out. So that is going to be x into y with 2. Okay. Then here is minus y square. Just a minute. Yes, x square plus y square. So I will write it. That's minus x square minus y square minus x square plus y square. So y square will get cancelled and minus 2x square will. So minus 2x square, right? So this is going to be, and now I can write it more simplified form, x times x square minus y square divided by x square plus y square plus you have, this is going to be not plus here, minus 4x cube y square divided by x square plus y square whole square. Okay, now what you can also observe is you can also show that fx at 0, 0, and you can also find out fy at 0, 0, which is required. Okay, without which you can't find the higher order derivative. Okay, now if you look at, okay, I'm just looking at carefully here in this in these terms. What I'm finding is in the first term or second term. Okay, if you look at carefully, the numerator degree is dominated is not dominate, means numerator degree is dominating the degree of the denominator. It's like denominator is of degree 2 and the numerator is of degree 3, because if you have x is right outside, so x you multiply, it's going to be of degree 3. Similarly, in the second term, if you look at the degree of the numerator is x cube into y square, that is 3 plus 2, that is 5. Degree of this term is 5. And the degree of the denominator is of degree, that if you take a square, it's going to be 4. So of course 5 is greater than 4. Similarly, 3 is greater than 2. Okay, similar here in this here. Okay, similarly in this case as well. Okay, so what you can observe from here, or you can also actually show that partial derivative at 0, 0, okay, because of the fact that f at 0, 0 is 0, you know, right? Okay, so you can also show that I can also verify. So this is going to be what? So if I write in the limit form as well, it is also very simple. Okay, if you want me, I can write it as limit h tends to 0, f of h comma 0 minus f at 0 comma 0 divided by h. Now, h comma 0 is a non-zero point. F at 0, 0 is 0. Okay, by definition. So this is going to be limit h tends to 0. So it's going to be f of h comma 0 by h. Okay. Now this is going to be limit h tends to 0. Now see, y is 0. Okay, x is h. You have to replace in the definition. Okay, so let me write down in this side what was the definition for x comma y is a non-zero point. Then it will be more clear. For that, what is f is? F is f of x comma y is equals to x into y divide into x square minus y square divided by x square plus y square. Now, from here, what is f of h comma 0? That is going to be Now see here in the in this term, this is going to be a h square by h square, that is 1. Replace y by 0, okay, and x by h. So it's going to be h square by h square, that is going to be 1. X is h, that is h, y is 0. So everything will go to 0. So it's f of h comma 0 is 0. Similarly, you can show, now similarly also you can show that fy at 0, 0 is 0 because of f of 0 comma k. If you find out, now your x is 0 and y is k, and you replace everything, what you will get is 0. So partial derivative f with respect to x at 0, 0 and also is now known to you, that is going to be 0. Okay. Now what is our aim is to now differentiate this fx partially with respect to y. Okay, so what is fyx at 0, 0 is going to be limit. So I am differentiating. So how will you read this? First you have differentiating partially with respect to, I'm just it is going to be I'm going to differentiate, so x, y. Okay, first with respect to x and then with respect to y. Okay, no, we have to, this is how this is dou square f by dou x dou y. So first you differentiate partially with respect to y and with respect, then with respect to x. This is how, right? If you write dou by dou x, so from left to right you have to go dou f by dou y. Okay, which we are representing fxy. Okay, so keep in that mind. Okay, this order is how. So from left to right. So first with respect to y, then with respect to x. Okay, okay. So now, so let me find out what is f y, or let me find out what is x y at 0, 0. What is the definition? When you know, you have already found fy, right? We are differentiating partially with respect to x, that case. So it's going to be limit h tends to 0. In the x direction we are differentiating. Fy at 0, 0 is going to be h comma 0 minus fy at 0, 0 divided by h. So fy at 0, 0 is 0, which we have found. Okay. Now, so this is equals to limit h tends to 0 fy at h comma 0 divided by h. Now, what you can find out now, fy at h comma 0. This is here. Okay, so fy at h comma 0, if I find here fy at h comma 0. Okay, that is going to be, so h, x is h and y is 0. So h time h square minus 0 square divided by h square plus 0 square. So h square will get cancelled. So this is going to be h minus. Now here 4 times h cube, right? H cube by, this is h to the power 4. Agree? Right? But y square is there. So second term is 0. Okay, because it's going to be h. And similar, okay, I will come back to that as well. So fy h comma 0 is h only. So this is going to be limit h tends to 0, h by h. So that is going to be 1. So fxy at 0, 0 value is 1. Now let's find out what is fyx at 0, 0. So by definition, that's going to be limit k tends to 0, because we are differentiating first with respect to x, then with respect to y. So finally, you are differentiating partially with respect to y. To whom? Fx. So fx you have already determined. In the direction of y, you are going to find out. So fx at 0, 0 divided by k. Now if we go back and check, okay, so what is fx at 0? Okay, fx at 0 comma k, what is the value? So x is 0 and y is k. So again, I am again by the similar argument, the second term will going to be 0 because of x is 0 here, so it will vanish every term. Now on the first, with respect to the first term, it is going to be k time minus k square divided by plus k square. So k square will get cancelled with minus sign, so minus k. Okay, so once you have this now, so this is going to be limit k tends to 0. It's going to be minus k minus 0 divided by k. So k will get cancelled, but with minus sign, so it's going to be minus 1. So, but this is not equals to 1, and which is nothing but the fxy at 0. Okay, so what it tells you that this this will this shows you that if you differentiate in a different order, okay, you may not get the same value at that point. Okay, so what you can means like how will you uh, make this sure that this should happen? Okay, what will make sure that this should happen? Okay, let's have that result which is known as mixed derivative theorem. Okay, so it says that if you have all the first order partial derivatives and the second order partial derivatives not only exist, we have already seen these are exist, right? Okay, so I want you to not memorize this theorem. Okay, I want you to look at the gist of this result. Okay, means how it will be applicable to your problem. What you have to look at is you have to differentiate, you have to see whether the first order partial derivatives and all the possible second order partial derivatives are exist and are continuous. So what is additional thing is the partial derivatives are continuous at that. Now it is your, now I'm leaving that point that you have to look at the problem. Okay, that previous problem what we have just now solved, that whether the continuity is missed somewhere. Okay, whether fx is not continuous or fy is not continuous or fxy is not continuous or fix, which one of them or which two of them or all of them are not continuous. Okay, at that point 0 0. Okay, that you can check, verify easily. Okay, so I'm that part I'm leaving you as an exercise. Okay, that where the continuity is or this condition is not followed. So if this condition is there, you can certainly tell that you can means you can differentiate in any order, whichever you want, and it will help you to get a simple expression. Okay, or like it will help you in analyzing the problem in a more simple way, because when you have the freedom to differentiate in any direction first, okay, means then you will look at the problem and look at means that in that way, that means like which first I should differentiate with the which variable. Okay, so for example, I will come out with this. Okay, I will come with that. Okay, you will have a freedom when you have one is have a freedom, right? Okay, any direction you differentiate first. Okay, then you differentiate with other, this will give you the same value. Okay, so this mixed derivative theorem tells you that if the first order partial derivative and the second order partial derivatives are exist and continuous, then this the order does not matter. Okay, so if you look at this example, W equals to X into Y plus E to the power Y by Y square plus 1. And I'm interested in WXY. Okay, first with respect to Y and then with respect to X. Now, since now you have to look at this W carefully. Okay, I'm writing it down here. So W is equals to X into Y plus E to the power Y divided by Y square plus 1. Yes. Okay. Right. So this is what the expression for W. Now, what I'm interested in WXY means dou square W by dou X dou. Okay. Whether I can go with any order or not. Okay. That we have to decide first. How will you decide? You have to look at the W expression carefully. Now, when you look at the W expression carefully, means you have to look at term wise. Okay. Now, when you look at the first term is very nice. X into Y, you can differentiate anyway. You are going to get the continuous function. It's a kind of polynomial, right? Of degree 2. Okay. Now, similarly, the second term now. Now, look at the second term. Second term is a rational function. And so a single variable in your case right now. So you are fortunate you are able to decide now what is the property of this function. So X is not explicitly coming. Y is not depending on X. So it is very simple to find out that this can be differentiated as many times as you want, because the denominator will never vanish, right? Y square plus 1 will never be 0 unless you will enter into the complex plane. Okay, so here we are in real valued functions. So this function is, the second term is also very nice. Okay, so which tells you that you can differentiate as many times as you want. Okay, so you will have the continuity, existence, and all higher order derivatives present here. Okay, now if you differentiate first with respect to Y, because see, you are interested in dou square W by dou X dou Y, then you have to differentiate both the term together. But if you differentiate dou square W by dou Y dou X, I will go in this way. Okay, what it will give me? Okay, if I go in this way, so I can differentiate, let's say first with respect to X. What is the derivative with respect to X? First term derivative is Y. Second term derivative is 0. And now if I differentiate with respect to Y, that is going to be 1. So this is how it makes your life simple. On the other hand, if you first differentiate with respect to Y, what will happen? The first term you have to differentiate with respect to Y, that is X. Plus second term, you have to solve, right? You have to solve. You can't leave in that here, right? When you want to show somewhere, okay, you have to write the complete solution. Okay, so it's going to be, you have to use the quotient rule. Okay, y square plus 1 whole square, and then f by g formula, and then you have to differentiate with respect to X. So in both the case, you will get the value is 1. Okay, so order does not matter in this case. So you are free to choose any way. So this way is very simple expression will lead. But here, if you go with this way, okay, you have to write at least the derivative of the second term once. Here you no need, right? But here it is required. So it gives you an extra work, which was not required actually. So, but to avoid that work, you have to have an insight into the function, okay, which tells you that this function has continuous derivatives, all order, and so on. How will you analyze? Based on the property of each term. Okay, you have to look at them carefully and then you have to decide. And this will all come from the practicing the problem. Okay, right. Okay, so I think these things are, I have to restart. Which one is you're talking about? Want it be 0?
Sir, am I audible?
Yes, you are.
Sir, that d2w by dx into dy, the one which we solved just now.
Here,
Yes, sir, the upper one. It would be 0, right?
this one.
Okay, no, sir, I got my mistake. Sorry, sir.
Because you are going to differentiate partially with respect to y. So that is going to be 1. Is that so, right?
Yes, sir, actually, I made a mistake there. Sorry, sir.
Okay. Okay. You have again, I think, differentiated with respect to x only. Okay. Right. So now we are in a position to define the differentiability of functions of two variables, and then we will end the lecture. Okay. Right. So now in the single variable case, what we have seen in a single variable case, when you talk about the differentiability, you have y equals to f of x. Right, you have incremented in the means like y plus delta y is equals to f of x plus delta x if you look at the fundamental definition, and then you have the increment in delta y is nothing but the difference of f of x plus delta x minus f of x. Then you divide both sides by delta x and then apply delta x tends to 0. Right, they made delta x tends to 0, delta y by delta x, which you have denoted by dy by dx, and that is going to be limit delta x tends to 0, f of x plus delta x minus f of x divided by delta x. Right, so this is how we have defined the definition of the derivative, fundamental definition in single variable case. What about the two variable? So in the two variable case, so you have z equals to f of x comma y. Function of two variables. Okay, and z is dependent, x and y are independent. Please note that. Okay, y is not depending on x. Okay, this is free. Okay, so it's a surface. Okay, it's a level surface when you have z equals to 1, and so when we do vector calculus, we will see that. Okay, now how will you decide the differentiability? So here, so at x naught, y naught, so you have to see the increment in z direction. How will you see? Your means like increment in the z direction is going to be f of, you have to increment in both the direction, x plus delta x comma y plus delta y. This is the you have incremented in both the direction. You will get another point on the surface, you can say, and that is going to be denoted by z plus delta z. So what will be the increment in z direction? That's going to be the difference between them, x plus delta x comma y plus delta y minus f of x comma y. Okay, now see delta z by delta x, if you divide by delta x and then letting delta x tends to 0, that will not work. Similarly, delta y, that will also not work because you have incremented in both the direction. It will neither land onto neither land onto the partial derivative with respect to x nor with respect to y. But what is the alternate? You can't put delta x comma delta y is tending to 0 both. It is also valid thing, right? It's not a definite thing. So what you will see, you have to see some of the x, it should satisfy some of the expression, means like it should be, means you have incremented in both direction. How this is going to be, this difference is going to be related in the both the term. Okay, both direction. So in each direction, if you fix a direction like x direction, suppose you fix it in x direction, so you can talk about the partial derivative with respect to x. If you fix the y direction, Okay, so if you this is x and y, and this is, let's just say, if you fix in the x direction, you are talking about the partial derivative with respect to x. Similarly, if you talk in the y direction, the partial derivative with respect to y. Okay, z is a depending on x and y. So what you can expect as a linear expression in terms of partial derivative in both the direction. Okay, in the both the directions. So fx delta x, fy delta y. Okay, this should have some simplified form. Okay, then you can work out some. Okay, right. So let me define the definition. Okay, differentiability, and then we will look at this in more detail. Okay, right. So I hope this is very clear that this is going to be the increment in the z direction. This is how you will look. Okay, right. Further, you can't go with like that previously, like delta x and delta. You have to keep one fixed direction. Okay, there's no other way when you apply the limit. Okay. So now, so a function z of f of x comma y is differentiable at x naught y naught. So always we talk about the differentiability at a point. Okay, if what will happen is if this partial derivative with respect to x at x naught y naught and partial derivative with respect to y at x naught y naught exists. So that is a minimum necessary requirement. Okay, and delta z satisfies an equation of the form this. So what is that delta z? I have just now spoken about that. That is going to be, now if in this term it is going to be f of x naught plus delta x comma y naught plus delta y minus f at x naught comma y naught. Okay, this is what the delta z. So how will you simplify it? So that's going to be simplified form. Is in the direction of this will come due to the in the direction of x, this term. This will come due to the due to the fact that you are going in the direction of delta y. You are differentiating with respect to y and multiply by delta y. And then sum of the terms epsilon 1 into epsilon 2. Okay, they are termed in such a way that both will tends to 0 as whenever delta x and delta y tends to 0. Okay, and this will also then help you to write down the function, the Taylor's theorem in function of two variables and three variables and so on. And it will now extend it for, you can also extend this definition to 3 variable as well. So, okay, so you have incorporated the partial derivative in both the directions. Okay, right. Now, if you take like along along x-axis, so delta y is 0. Along y-axis, delta x is 0. Okay, and then you have the partial derivative definition. Yes, am I clear? Right? If you look at, so again I'm repeating. Okay, if you look at along the line or along x-axis, okay, along x-axis, there is no increment in y, so this term will vanish. Okay, and this term will also, delta y is 0, this term is also not there. Okay, so these two terms will vanish, so only remaining with this, and you divide by delta x both side and then apply limit delta x tends to 0, which will lead to the fx partial derivative with respect to x at x naught y. Similarly, along the y-axis, delta x is 0. This term will vanish in that case. These two terms will get vanished. And then divide both sides by delta y and then apply limit delta y tends to 0. And that will tends to the partial derivative with respect to y at x naught. Okay. So this means like when you lie down in a particular direction. But as we have seen in the limit case even, that reaching towards the point x naught y naught may not be the straight line. It may reach along any path, any spiral path, or any parabolic, any line, straight line, and so on. There are infinitely many paths. Okay, now see, so this is, so but this is not you are not means like it is not easy to check every time that this whether this delta z expression will satisfy this or not. So we have a very important result which says that this actually happens, but that is going to be the sufficient condition because it adds one more condition. Okay, that will add one more condition of the partial derivatives. Okay, and then you can say that that's going to be the differentiable function. Okay, so this is a this is a definition of differentiability. Okay, so again I'm going to mention now the result, which you can also treat as a, you can say, definition, but not as a standard definition, because that will give you the sufficient condition. Again I'm telling you, you will find out once I mention that, because here you are only mentioning the existence of the first partial derivative. Okay, in that result you will see the continuity of these first partial derivatives added. So if along with the existence of the first partial derivative, if you add the continuity of them, if you verify that first order partial derivatives are also continuous at that point, okay, then you can say the differentiability is there. Okay, so this is what I have just now told you. So this is a very, you can look at that, this is a very big term, but what we are interested in, again, the gist of the result. Okay, or you can say in the terms of corollary. Okay, so what it says that, let's say first partial derivatives are defined, okay, throughout an open region R containing the point x0 and y0, and that fx and fy are continuous. Okay, means first partial derivatives exist at the point x0, y0, and they are continuous at x0, y. Then this change will satisfy this. Okay, so means this says that the function is differentiable. So what is added here is fx and fy are continuous at x0, y0 in addition to that. Okay, right. So what is the corollary here? So if the partial derivatives fx and fy of a function are continuous throughout an open region R, then f is differentiable at every point of. Okay, so this, if you you have talked about a point, now you can talk about now on the reason. So on the reason means like on the domain, if it is like if all the partial derivatives are continuous throughout an open region R, means at every point the functions these partial derivatives are continuous, then it is differentiable also at every point. So whenever you want to check the differentiability of certain function of two variables, okay, then you can simply check the continuity of the first partial derivative. If that is there, differentiability. So this result you can extend into the any dimension now. So three variables, you have all the first partial derivative fx, fy, and fz are continuous, then that function is differentiable. So you can add one more direction, you can add as many directions you want. Okay, and now in that case, the finally that will give you that differentiability implies continuity, and that is very simple to see. Okay, so you try to figure it out, we will see in the next lecture. Okay, so if you have any question, you can ask. Yes, no doubts. Okay, okay, then that's ending now here. Yes,
Hello, am I audible?
yes, yes.
Sir, can there be a chance that for a function f of x exists, f of y not exists? Like the function is, we can do partial differentiation with respect to x, but not with respect to y.
Yeah, it can be
Okay.
possible. Yeah, that can be there. Means like first, like partial derivative with respect to x will exist, but with respect to y will not exist. It is possible. You can look at some of the rational function like x by y. Okay, we can look at the function x by y and try to check it out at 0, 0.
Yes, sir.
Okay,
And sir,
forcefully you define at 0, 0.0 value. Okay, x by y is for x into y or x comma y is non-zero whenever, and x and y are 0. Both means origin. At origin, the value is 0. And x and whenever it's not origin, then it is x by y. I think so.
and
That should work. Even continuity is not there. Or means like existence of the limit itself not there. And, whenever you are talking about the partial derivative with respect to y, I think try to figure it out.
yes, sir. Sir,
If
will this
if it
light
is
be
still
shared with us?
challengeable, suppose it is still challengeable, you can also look at x by, you can increase one more power, x by y square, you can also look at. Okay, suppose sometime like y will get cancelled. I have not solved it out, so it may be possible that somewhere it is more possible that fy also does exist. I'm not able to look at it right now. F at 0 comma k is 0. Oh, so 0. F at 0, 0 is 0. So fy derivative exists at 0. Yeah. Yes, I think so. It is exists, right? Fy derivative exists, but it is not continuous fy, right? At 0, 0. This is what your question, right?
Yeah, like was it can get
Uh,
example?
hmm?
Yeah, yeah. Like we can find that kind of example.
Or you can simply, why you are involving x even. You can take f of x comma y is 1 by y. Simple.
By why?
Because
Yeah, exactly.
x is making it 0. You can remove that. 2 by y, 3 by y. Okay.
And sir, will these lights be shared with us?
I will be sharing this recorded video. Slides, I don't know. Slides I have to means like extract it and do it. Okay, because in the open board I have to see. Okay.
Okay. Thank you, sir.
I think recorded videos are I think you can access,
Yeah,
right?
they are available. Yeah.
Huh. Okay. Okay. Is there any other question? Okay, fine. Thank you.